Hello, everyone. Thanks for joining us again today. My name's Charles Rice. I'm your host. We're going to be talking about sound intensity, measuring it with P probe versus a PV probe. Actually, you know what? That says PU probe. Maybe that's a question I can ask our presenters today, Steph Nelson and Raj Ipili. They're going to be presenting for us today this subject. Hey, before you guys maybe introduce yourself, maybe Steph, you want to clear that up for me? I was wondering why it says PU probe instead of PV probe.
Yeah, absolutely. So when you're doing acoustics, U is the variable associated with particle velocity. Some people use the PV, V for velocity, but U is specifically particle velocity, which is an important distinction that we have to make for the different types of probes. So it's both. TestLab uses PV, some people use PU.
Okay. Thanks for clearing that up. Appreciate it. So if you don't know, that's Steph Nelson. She's an application engineer for Siemens SimCenter TestLab products. She's also joined by Raj. You want to say hello, Raj?
Hello, everybody. My name is Raj Ipili. I'm in the customer support team supporting the SimCenter Test Lab and the SCADAS hardware product. Today, we have got a good webinar here with some live activity. So I think you are going to enjoy it.
Yeah, it looks exciting. I'm looking forward to it. I love this live demos. They're always exciting to watch one way or the other.
That's true.
I've been there, guys. I've been there. So don't worry. I've been there. Well, with that out of the way, Steph, I think we can give our attention to you to get us started.
Sure, thanks. Thanks, everyone. As Charles mentioned, I'm an applications engineer with Siemens. It'll be fun to kind of discuss what sound intensity is and two different instrumentation you can use for measuring sound intensity. So before we even get into sound intensity, there's one thing we have to get some common vocabulary. And the most common thing you'll see, it's in a bunch of our presentations, and it's this thing called the source path receiver paradigm. So on one end, we have the source. So this is what's going to be generating the actual noise. This will be, if you're in automotive, this could be like a gear or a fan or something like that. And the source will have a magnitude and a direction. But when you want to quantify how much energy is coming out of the source, we use something called sound power. Sound power is very unique to the actual energy coming from the source. And the reason that it's unique is because, as you know, when sound travels, it goes through some path. And the path can affect how sound is heard. So if you're in a high school gym, for example, sound might be louder and more reverberant. You're going to hear it differently. You're going to measure sound pressure differently, which most of you will probably be familiar with, than if you were, let's say, in a really quiet library that's full of carpet and acoustic absorption material. So the path can really alter how the source is heard. And at the very end, we have the receiver. So if you've ever done sound measurements, you've probably heard of sound pressure. This is what's measured at the receiver end. Sound pressure is great, but like I just mentioned, it can be sometimes not a representative measurement of the actual sound energy that's coming out of your source. And usually when we're doing products, we want to know exactly what energy is coming out because we don't always know where it's going to be emanating from, what the path characteristics are going to be like. So you have to kind of understand the difference between these because there's a massive difference between the sound pressure, the sound power, and then something called sound intensity, which we'll get to. So this is my colleague's favorite analogy. It's not my favorite, but it is good, so I will get to it. They like to use what's called the heat analogy for defining the difference between sound pressure and sound power and then sound intensity. So if you have a specific, let's say a heater in the room, you know that the heat output is going to be in some type of power in watts. And we also measure sound power in watts as well. So the heat output is going to output some temperature. You know how much power and energy it's going to output. But what you don't know is where in the room, if you took a thermometer and you were to measure where you are in the room, that temperature is going to be different because of the path fluctuations. So we like to kind of define the difference with sound power and sound pressure as you're taking a thermometer and you're walking around the room and you're going to get different temperatures at different portions of the room, but the heater is always going to be outputting the same exact amount of heat. And it kind of works the same. So if you've got a vacuum cleaner, the vacuum cleaner is going to be outputting the same amount of sound power in watts again, but depending on where you are in that room, you're going to get a different sound pressure. So sound pressure, summed up kind of nice, is the result. It's what we hear, it's what we measure, and then sound power is the cause. It's the quantity. Where that might be confusing is sound intensity. Not familiar with sound intensity at all. You might be wondering how those two connect. So we have our temperature and our power, and we like to use sound intensity as sort of the heat flow. So it's the direction of where the heat is emanating from and the magnitude. And you'll notice that I used magnitude and direction, and if you were familiar with any of your physics classes, that might sound like the definition of a vector. And that's exactly what sound intensity is. Sound intensity would be like the heat flow in this analogy. And once again, I mentioned vector. Sound intensity is a vector. It's a vector quantity. It has magnitude and direction. It's different from sound power. I've got this nice little graphic down here that actually uses one of Siemens's other instrumentation products. It's called the sound brush, if you're familiar with that. So sound pressure is just the magnitude. You can see that these little red spots here show the amplitude of what's being measured, but it doesn't show the direction. It doesn't show where that sound power is emanating from. But the sound intensity offers both quantities. So that's kind of one of the nice things. If you're trying to quiet a noise source, but you need to figure out how it's actually getting out into the world to be heard, sound intensity might be a really nice measurement for you. So it's technically defined as the average rate of sound energy in an area. When we measure sound intensity, if you do the calculation, it's watts per meter squared. It's the energy over an entire area. So when we do our intensity analysis measurements, which we will later in this demo, hopefully if everything goes well, you'll see that we're measuring over little specific area blocks. And that's typically how sound intensity measurements are done. So intensity is obviously dependent on the source. Not everything radiates sound equally, and it doesn't necessarily go in the same directions. You'll know that if you've ever worked on an engine at all. It's kind of crazy exactly where the sound is coming from and the paths that it chooses to take. Usually when we do sound intensity analysis and measurements, we're either trying to localize where sound is coming from. So we're trying to find out exactly where these hotspots are, or we're trying to find the direction that the sound is emanating through. So the sound path that it's going to be traveling. Because if we know the path, we can usually try to attack the sound problem in that vicinity. So the intensity probe, I've got one here. I have a couple different probes. Obviously, we talked about there's going to be two different probes. So I've got this nice little intensity probe here. And it comes with 2 microphones. There's a reason for that. You'll notice that sound power and sound pressure are typically measured with 1 microphone. So it's got 2 microphones. There's a preamplifier here to help boost the signal and a preamplifier here. And then it's sort of difficult to see. We've got 1 microphone here and 1 microphone here. And then this little black thing in the middle is called a spacer. And there's reasons we use different spacers, and there's reasons we use 2 different microphones. So the reason we use 2 different microphones, these are phase matched microphones, is because we are trying to measure the speed of the wave. We're trying to figure out how fast the wave is going so we can get that magnitude and direction, the direction being the important part. So what we do is we use 2 microphones that are facing towards each other and they're phase matched. So we can tell that when a sound wave hits 1 microphone, the time difference it takes for the sound wave to hit another microphone. And then obviously the software or whatever type of software you're using can back calculate that. So if you have there's a space in between because it has to relate to frequency. But if you have 2 microphones that are facing each other and you have the direction of the wave crossing over one and then the other, we say that you'll measure all of the intensity, or 1 + 1 of the intensity. If the wave's traveling backwards, you'll get a negative intensity because it's like a vector, so it's got direction. So that's two kind of important things. This is why we use 2 microphones. Now, one of the main differences you'll see in the presentation today is the PU, the particle velocity probe, does not use 2 microphones. But the PP, the pressure, or the common, I would say, sound intensity probe does use these 2 microphones. If you were to measure sound, but you had the wave coming inwards, it would hit both these microphones at the same time, and your intensity measurement would be 0. So it's really important that you're holding the intensity probe, specifically this type of intensity probe, in the right direction of where sound is coming from. And a lot of the test lab software will actually do live updates while you're doing it to make sure that you can scan and kind of get a good idea of the direction of the sound that you're catching most of that intensity. Lastly, if your microphone is off a little bit, you can start getting into some crazy math about how much intensity you'll actually be measuring. It'll be like a function of the angles depending on how you're holding it. So it's at like a 45-degree angle. So it's really important that you're holding the probe directly parallel to the noise source. If it's perpendicular or orthogonal, you're going to end up with 0 intensity, and that's going to affect your intensity measurement. pros and cons to using the intensity probe, which is this 2-microphone probe, over the PU probe. And the PU probes are in these little boxes right now because they're really fragile. So until we actually start measuring, I'm going to keep them safe. But the PU probe looks like this. So there's no preamps or microphones or anything else that kind of makes it a little more confusing. It's a little easier to use. Okay. So we talked about spacers, and the reason for that spacer is because it affects the frequency range that you can measure. To get the lower frequency, you have to be able to have a large space. You can see down here this green mic 1, the distance between mic 1 and mic 2, and that's because low frequency waves have such a longer wavelength. If you have those microphones too close together, it can't actually pick up those low frequency wavelengths. So if you're like in the 10 of hertz, I mean that the wavelength of that is massively long. You need a good amount of space between the two probes. We put the spacers in because it's an exact measurement. It gets us exactly to the spacing we want, so we can measure these frequency ranges. This is very unique to the sound intensity probe, not the PU probe, as we'll go on to find out. The PU probe, as you saw, it didn't have 2 microphones and it doesn't need a spacer. But if you're using the sound intensity probe, you need to have the right spacer for the right frequency range that you're interested in. So this means you kind of have to have an idea of the sound range that you're looking for. So if you're doing high frequency gear measurements, you need to know that versus low frequency engine noise, because if you have the wrong spacer in, it won't pick those up. So here's kind of as you'll notice, the closer together those microphones are, the higher in frequency you can measure. So it's important that you kind of consult. There's tons of websites online that'll help you calculate this, and there's a place, if you're running the TestLab software, there's a place to put in this microphone spacer so that you know exactly what you're getting. So it's just kind of a nice check to double check if you're using an intensity probe. That if you've ever used one and you're like, I don't know what the spacer is for, this is what it's for. So there's a couple ways you can measure sound power with sound intensity. We can measure sound intensity and we can also measure sound power. And I talked about how sound power is the source. And the way you can do that is you can build usually a little grid. And this little grid you build around your test article. There's a standard specifically that defines this. It's the ISO 9614 standard. This will give you sound power. You can also use this grid method to measure sound intensity and sound localization. So the idea is that I have sort of my little speaker set up here, and we'll mess around with this in a bit. And I actually don't have a gridded box, but I did make it's kind of hard to see on the camera. I did make little measurements, and I have like a tiny little grid system I'm going to measure in and around. And ideally, you would want maybe some wire or some fishing line to create an actual grid box so you can get precise measurements. And that's sort of what's in this picture here. So when you're doing sound power from sound intensity, there's 2 methods you can do. You can do a scanning method where you take the probe and you scan each side for about 30 seconds, or you can do what's called a point-to-point method. In this method, you would use each individual box, like I mentioned in my sort of poorly seen grid system, but each individual box would get like its own 30-second measurement. And then when you sum over the surfaces and multiply that by the area, you back out, we talked about sound intensity as watts per meter squared. If you multiply by the meter squared and you sum that together, you end up with sound power. So it's a nice method of doing that. So this is an example. We've got a speaker and I've got a little grid system on top of it. This could be wire, it could be fishing line, it could be whatever. It's usually a physical system just so that it's easier for engineers to keep track of where they're measuring. And you can slowly scan across the surface and end up with a averaged intensity spectrum and then multiply that by the surface area, and then we have a sound power level. So hypothetically, this would be 104 dB. Now, sometimes you need to measure all sides of the test article, whatever you're testing, because you don't know exactly where that sound's emanating from. And in that case, you would need to do measurements on all the sides. But in this case, we're pretty confident that the sound is supposed to be directed outwards because it's a speaker. So this would be an easy way to measure sound power. Now, sound localization, this is where sound intensity really comes into play. Here you would take a measurement at one dot, and then a measurement at another, and then a measurement at another, and that's what we're going to do today. And then you're going to have different sound measurements at every single location. And then once you do this, you'll get something really neat. You'll get something that you can also back out sound power this way, but you'll get something that looks like this. So you'll get an intensity map. And this is really nice because now you can see that it looks like on this system, most of the intensity is coming out of this tweeter section and not this subsection. So depending on what type of noise was played out of the speaker, I don't particularly know. I'm going to guess it's more high frequency since the subwoofer isn't really being utilized. Now, if you have something more complicated, this can be really useful to trying to figure out where your source is coming at what frequency. So if you want to isolate specific target frequency problems and find where those are coming from, source localization can be really great. Okay, so we mentioned that there's two different types of probes. We have the PP probe, and once again, that PP stands for pressure. It's called pressure because we have two microphones. We've got one microphone and another microphone. And then we have the PU probe. I've got one, that's a 3D one, we don't need that. I've got one here. And as Charles mentioned, the U, when you're doing in the sound literature, U is used for particle velocity. So that's why they call it PU. It also can be PV. The TestLab software, once again, refers to it as PV. So this probe's pretty simple. It plugs right into a BNC. And then while I'm down here, I'll show you some of this setup. So right now I've got a Scatus XS unit. It's connected to the two different types of probes. One of them is going to the signal conditioner for the PU probe. So if I turn that on, it's got two channels, you'll notice. One of them is for the microphone element, and one of them is for the particle velocity measurement element. So that's what those two channels are here. And then I've got my sound intensity probe that's also connected to my Scatus XS. And this one also has two channels for both microphones. This one's nice. It's got a lot of fun buttons. They can help you do, if you're measuring a lot of points in a lab, this is a little remote that can help you skip through menus on TestLab and make your testing a little more efficient. So if you're looking for that, this might be something for you. So I discussed the PP probe. We got the spacer, the microphones, and the preamps. So the two microphones are used to measure the speed of the wave. We talked about how the spacer is required because you need to be able to capture specific frequencies based on wavelengths. This can be used for localization and scanning. The PU probe can also be localization and scanning. But one important distinction is this is pretty well known in general in terms of testing for the ISO standards. There's a lot of ISO standards associated with using the PP probe. And Raj, you can chime in and correct me if I'm wrong, but I don't believe there's ISO standards that specifically define the PV or the PU probe. Is that correct?
Correct, Steph. And that is to my
Okay.
knowledge also.
So if you're trying to just nail a standard and you want equipment that follows that, this might be a probe for you. That's a pro, I would say, of this probe. So the PU probe, if you're wondering, it doesn't have two microphones. So how does it work? It has a MEMS sensor. So there's these two little wires, and they're resistive elements that actually measure the particle velocity of the wave as it travels through. So as the sound wave hits one and then the other, the resistance between these two change. And because the resistance changes and it's directly proportional to the speed of the wave, we can measure the particle velocity. So this probe actually directly measures particle velocity compared to the PP probe, which has to do kind of a back calculation between two microphones. The nice difference between the PP probe and the PU probe is there's no spacer. You can get a broadband signal right out of measuring with the PU probe. And by broadband, I mean that you can, measure from low frequencies to high frequencies. You don't have to worry about getting the exact right spacer in there to get your frequency done. So if you don't know what your sound source looks like, this might be a better instrumentation for you to use. It has a frequency-dependent calibration. So when you get these probes, they come with a curve, some type of frequency curve. That the probe is more sensitive to certain frequencies than the other, so it weights them differently. And if you get a curve like that, you can input that right into TestLab so that your whole calibration is good to go. Another thing that this probe does, technically the PP probe does this too, but this probe does it way easier, is it has a 3D probe. So that's this guy right here. So this will actually measure the sound intensity vectors in all directions. It has 3 of these sensors that are in orthogonal positions to one another. So it makes it really easy to do a 3D measurement of that. You can do the same thing with the sound intensity probe, but as you imagine, you will have to take 2 microphones and put them in directions here and directions here to get all your directions. They do make that, but it gets very complicated. So if you're looking for something simple, this 3D probe might be for you. As I mentioned when I was taking it out and why it's been sitting in this nice little red box, it is more fragile than the PP probe. It's very fragile. It's got the very small, too thin wires. You know, we don't want to drop it or anything like that. It can damage the sensor, and it's, as you can imagine, because you're in engineering, all these sensors are very expensive. Okay, I did a lot of talking. Hopefully you're still with me. Now we can do sort of a quick demo in Test Lab to show the differences between these two. I'm going to jump right over to Test Lab. Okay, so I've opened the sound intensity package in Test Lab. And if I go over to geometry, this is really important. You can start creating your geometry to sort of match this test article here. Now, despite the fact that my sound source is cylindrical, my grid system, the actual surface area that I'm measuring, is rectangular. So we want to build a rectangular geometry because that's where the calculation is going to be performed. So I'm going to do that really quickly. You can, if you've ever used Test Lab, you can make geometry by adding in surfaces and nodes, but there's an even quicker method to do it. If you're doing sound intensity, you can hit this button right here that says Generate Acoustic Mesh. So if I click that, I have a bunch of stuff that comes up. So these are the divisions. These are how many boxes you're going to make in every direction. So in this case, I'm going to make 3 boxes on the front. We'll divide these into 3. 3 boxes on the back. 1 box on the right, 1 on the left, and then 3 on the top and 3 on the bottom. I can choose between using local coordinates and global coordinates. I'm going to stick with local coordinates right now because I think that's going to be easier for measuring later.
Sorry,
What's that?
Are you going to measure the bottom also?
Oh, excellent point. I am not going to be measuring the bottom. Thank you, Raj. I have this on a little piece of plywood, my speaker. So because it's not being measured on the bottom, if I were to accidentally click this, when it does the calculations, when it does those localization maps, those heat maps, it actually interpolates between the surfaces. So if I had this checked on, I could get the wrong result. Thank you. That's an excellent point. So I'm going to add in, I've got my one side is roughly 10 inches. And my other side's roughly 16 inches. So I'm going to put that in meters. And I thought this was neat because this was something I didn't know. If you're doing scanning, you can come down here and choose where you'd like to start versus how you'd like to scan. So I can decide I want to go up and down if I'm doing localization, or I can go across and then down like one direction. I can also choose if I want to go left to right or up and down. This is fine for me for now, so I'm just going to leave this. I hit create and then close out.
So here, sorry to interrupt, but what is the difference between local coordinates and the global coordinate system there?
Yeah, so I can actually show you by going to model nodes and Euler angles. So the difference between local and global coordinates, if I go back to generate acoustic mesh, the local coordinates will always make sure that you're measuring normal to the measurement surface. It'll always assume that. The global coordinate system will not. You have to make sure that you have to understand exactly where you're measuring in that space. But the local coordinate system assumes that you're measuring perpendicular to that surface, which is nice, and that's also what we're doing, so we can leave that on.
Oh, okay, I see. So what that means is basically that the z direction will always be the normal to the surface if we choose the local coordinate system. And then if we choose the global, then they will just be in the global x, y, z directions for all surfaces as shown on the left-hand side there.
Yes, that sounds right to me. I'm going to hit close, otherwise I'm going to accidentally make 2 geometries. So this is what our little geometry system looks like. On one side of the speaker, I have 1 node, 1 measurement point. So I'm only going to be measuring once. On this side of the speaker, my test article, I'm going to be measuring 3 times. I'm actually not going to measure all of these surfaces all over for you guys. We did some measurements ahead of time because I think measuring them is a couple times is good enough to get the point across. Okay, if I go into channel setup. Okay, so we've got the channel setup. Like I mentioned, I've got two things connected to my probes here, or to my SCADAS unit here. I've got the PU probe first, I've got the microphone channel and the particle velocity channel, and then next I've got my PP probe connected. I've got my mic 1 and mic 2. So the PP probe uses ICP. If you don't have this selected, when you go to the acquisition setup, you will see that you don't get any noise and it doesn't work, and we don't want that. So that's one very easy way to do that. The PU probe uses voltage AC. The reason for that is it has its own signal conditioner. That's the big, beautiful, shiny box in the corner. So we don't have to worry about using ICP. If you've never heard of ICP before, ICP is actually a trademarked name. If you want the untrademarked name, it's IEPE. I've got my sensitivities plugged in. You'll notice that one big difference between pressure here and the difference here is I have particle velocity. Now there's an option for velocity down in the quantity section, but you want to make sure you select particle velocity because TestLab will interpret that a little bit differently when it does the measurements. So that's one thing that you want to make sure you have properly selected. The rest of this looks good to me. Hopefully it looks good to all you guys. There's a calibration tab. Our stuff's already calibrated. We don't need to worry about that. But if you did need to calibrate, they make special calibrators for these instruments. So that's something you can do here. Okay, now we're going to make sure that everything is good to go. I'm going to start really quickly by making a measurement with the PP probe. So I want to make sure that my microphones are on. Make sure everything's working. I'm making little snap noises, and I'm seeming to get stuff on the system. Let's see if mic 2 works. Looks good to me.
Yep, looks good.
Okay, so all I've done here is I've gone up and I've selected my channels. I do want to change some of these acquisition parameters. My bandwidth, I'm using a smaller spacer, so I'm 6400 is probably good enough for me. My resolution, 12 hertz resolution is really poor resolution. You can pick that if you're worried about data, but we have the ability to go a little finer in resolution. So we're going to do a 1 hertz resolution. This is going to make sure that we can see everything on a 1 hertz per basis. Every frequency that we get out of our measurement system will be on a 1 hertz axis. So it'll be 1000, 1001, 1002. So we have a lot more resolution with that. Panning window looks good. All this stuff looks good to me. I'm going to go on to the sound intensity setup. Now this might look really overwhelming. There's a bunch of stuff you can go through. The first thing here is that TestLab has those ISO standards built in, so you can pick which one you're measuring to. So let's say I'm measuring to this one. It also has its accuracy built in. If you ever read an ISO standard, they usually come with 3 different types of accuracy. There's a precision. So this is like something if you wanted to put it on a product, you had a high precision laboratory measurements. If you're doing engineering, this is probably what most of you, if you're on the call today, are doing. Or if you just want to do a quick, scan, but you don't have the special equipment and you're not in a special room, you would use a survey method. So the accuracy is over here. Bias factor is built into these accuracies. You can change that. You can change how your node numbering is done. And then this, I feel like it's a little non-intuitive. We're going to create a probe, but to make it visual, you have to come up here and hit this little show hide binoculars. And when you do, the screen becomes really nice. So I mentioned that TestLab calls it a PV probe, particle velocity probe. So we have 2 probes. I'm starting with the sound intensity probe, the pressure probe. I'm going to hit create. And you'll notice, if you did this right, that your geometry defaults in TestLab, it defaults to like the very end of this list, but you should create that first before you get to the sound intensity setup, because if you don't, TestLab may not link your geometry to your probe. So in this case, I've got my point identification. It starts at front 1 and it's got the right direction. We know that this is going to be accurate. The channels are in the wrong ones. These are for the PU probe, so I'm going to swap these really quickly. TestLab's realizing that that's great. My spacer I'm using, I'm going to change, it's about 1 inch. So I'm going to enter that. This is going to help with the frequency calibration. Raj, we don't need to do anything with phase correction load, right?
Yeah, we are already using the phase matched microphone, so it's good to do the phase calibration, but here we don't have that intensity calibrated to do that, so we are going to skip that step. Our phase matched microphones are good.
And you'll notice here too, the available range, because I've typed in this spacer. So if I type in something different, like 10, now my frequency range is way lower because that's a huge spacer. So TestLab automatically will calculate what frequency range you can get. And there's different spacers that come with the probes. I've got a ton I can show you towards the end. So we've added the probe. Everything looks good, except for there's a warning down here. It wants us to turn off, is it this guy? This guy. It's saying that it can't measure this one. So that's good. But I want to measure sound intensity and sound pressure. If you want to, the add-ins for this one, it's one of them is missing. It's the ANSI octave filtering add-ins. It's actually can be turned on right here. If you're doing PP probes, you'll want to turn that on. It's one of the ISO standards that helps funnel your data into octaves using time-based domain filtering instead of frequency-based domain filtering. Really useful, and we're going to use this at the end when we start doing intensity analysis. These settings were pulled from our acquisition setup. These all look good to me. And as long as I don't have any warning messages, I think I can go on to measure. Oh, actually, there's one thing I did want to do. I forgot to do. If you're in the geometry setup, there's one cool thing you can do. You can hit import photo to mesh. I actually took some photos from the sides, so I'll do the left side. And I'm going to browse to my photo. This will help if you want to remember like exactly what you're looking at. So this is nice too. And then up here, these are your step sizes for adjusting the picture. I'm just going to make them a little smaller. So I can scoot it over. I can make it bigger. So now I know what's on that side. I'm going to hit close. That looks good. I'm going to add one more. Import photo. You don't have to do this. This is completely optional. It just helps when you're measuring to remember what you're looking at. I'm going to make this a little bigger.
And when you're presenting the results, it's nice to have a picture behind the localization result, for example.
Yes,
so that,
it is very nice. Okay, that looks good to me. Okay, so if we go to measure now, you'll see that I've got my pictures on my side, so I know exactly where my left is and where my right is. And then I can start measuring. So I'm going to arm my system. Okay. And this might be loud, depends on where you are. I'm going to turn my speaker on real quick. And I've got some white noise I'm going to play out of it.
Yeah, it sounds good.
Perfect. It wants me to start on this little node here. So I've got my space marked out. This little black dot I'm going to align it with. And I'm going to start measuring there. Whoa. Now, Raj, would you like to explain why there's some red and some green up here in this octave plot and what these plots are?
Yeah. Okay. So what you see here is in the top left-hand side display that is showing the instantaneous spectrum and the averaged intensity spectrum. And on the top right-hand side, you see them in the octave format. And when you see it in the octave, you can see that some of the octaves, they are showing in red and some of them are green. What the red means is that at that frequency, the intensity is in the opposite direction of the way you are measuring it. So you may have noticed that Steph was not exactly pointing the right direction with the intensity probe. That gives us an idea that you have to flip it. So change the orientation of the microphones in the PP probe such that you can get like a green bars then. So we are measuring negative intensity. What we want to measure is positive intensity. So she has to rotate the intensity probe by 180 degrees, basically.
So I'm going to retake that measurement real quick, and I'm going to flip the intensity probe. So I'm just going to hit play. Oh, I should replay my white noise, shouldn't I? Gonna retake that one more time.
There you go. Now you can see that this looks really great. All the bars are green. At low frequencies, some of them are red. A couple of bars are red, but that happens because there is reflections in the room and things like that.
I'm sliding off my chair here, trying to make sure I can reach both. And I also am measuring semi in the middle of this box. If I had a grid system, it would be more apparent, but I'm trying to measure exactly where these little nodes are. We decided to measure for a long time.
Did you accept the previous one? Okay.
It did. Did it not accept? Okay. No, it looks like it did.
Yeah, it did. It did. Sorry, it just updated a little late.
Oh. And the last one.
You can see that as she's moving that intensity probe, like the points corresponding to showing in the geometry, they are updating. So it was front 1 to start with, now it became front 2 and front 3, right? So there has to be one-to-one correspondence between what you are measuring to where you are placing that in the geometry.
Okay, so I'm going to disarm. That's going to let me change the side I want to measure on. I'm going to do this back side now. I'm going to play some more noise, arm it, and then we will be done with the PP probe.
So the nice thing about this view is you can get a real indication of the quality of the measurements live during the acquisition. So if you turn the way Steph has set up, you can clearly see where you are doing the measurements, and then you can see the live spectrum. And actually, if we had measured the phase calibration, if we had done the phase calibration and such, we'll have an upper and lower limit for the intensity curves. And there we can see that the intensity is a good measurement. That is kind of like measure of our quality of the data. The upper limit for the intensity is the sound pressure, and that's what you see the pink line in the right side display there in the octave, and that is the upper limit. All your intensity should be lower than the upper limit. Based on the instrumentation used, there can be a lower limit curve also, which we didn't perform the phase calibration, so that's why it is not showing up here. Okay.
Perfect. So now we can go to validate. This will show us all the measurements we have. So obviously we have lots of surfaces, but it says the only place we've taken measurements on are the front 3 nodes and the left. And I can highlight all of them here. If this looks kind of flat to you, that's good because we're playing white noise, so it should look pretty flat. We shouldn't have a lot of peaks and stuff in this data. These are just auto powers, FFTs of the data we took at each measurement location. And that's exactly what I would expect them to look like. So that's good. So you can use validate really quick to do that here. To make all the really cool color plots, I'll show you how to make them, although this data won't make a ton of sense because we didn't measure the other sides. I do have data where that is measured on this particular test article, so I'll show you that too. If you go to intensity analysis, I want to add my data in, so I'm going to click these 3 dots, make sure I'm on section 1, all runs. It looks like that's good. I'm going to click add. You can come down to this little binocular guy here, and it'll pull this open. This will also show us again what we've measured. So we've calculated the front meshes. We've measured the intensity and the sound pressure of the front 3 nodes, and we've calculated the sound power. So that's kind of what you can see individually here. And then we did the one on the side. So that's all we've done so far. And then there's this CRIT 1B and these CRIT 2Cs. If you read the ISO standards, these are explained there. This isn't an ISO presentation, so we don't have a lot of time to get to that unless people have questions. So now if I click this button, it says add all the third octaves. We're going to do that. There's an X right now because none of them have been calculated. So then I can come down and hit calculate bands. And you'll see I've got a little intensity graph. This data, this is the sound intensity for all the different octaves. So this is the 1/3 octave at 63 Hertz, the 1/8 octave, and I can scroll down and see where all these are. This data might not make a ton of sense because once again, there's all this blue space because it interpolates between the different surfaces and we didn't measure those surfaces. So it says that there's no sound up there. Once we do though, we would get a more complete picture.
Excellent point, Steph.
Yep, we get something nice like this. Okay, we'll do 2 measurements with the PEU probe because you guys understand how to measure, I think. So I'm going to go back to my intensity setup. I'm going to delete this probe now. I'm going to grab the end of the PEU probe. This one's really basic, if you can see here. Just going to plug this guy right in. Should be good to go. And then I'm going to add a PV probe. So create new probe. This one automatically sends the inputs 1 and 2, and it's already got the geometry associated. There's one little orange box here. It says it can't do time-based processing. That's okay. We're just going to unclick that, and then we are good to go. So I'm going to play some white noise again.
So Steph, do you want to create a new section or do you want to just override the existing data? Which way you want?
Oh, that's a very good point. We'll call this one PV. I'm very excited to do measurements, Raj. Thanks for reminding me.
I can see that, yeah.
I'm just going to do one quick measurement on this back side here, just so you guys can get an idea. We'll click arm. Oh, no, I won't because I'm measuring on the front, and that's not what we want. Okay, there we go. Now it says left. Play some white noise again. Hold it at roughly that center black dot and click go. And I'm all set. So now I can turn my signal conditioner off. Put my PEU probe securely back where it's supposed to be. Oh, I did another one on accident. That's okay. That's what happens when you don't disarm your system. some test engineering tricks. It says we've only measured 1 auto power. That's good. Go to intensity analysis. We have all the data from before. We have to re-add in this new data. So we're going to go to section PV. I'm going to use my first run because my second one was an accident. I'm going to hit replace, double check and make sure that all I've done is the left. I've measured and then I've calculated all of these. And then I'll go back down to, do I need to delete these first? Can delete them all one by one. I'll hit recalculate. And if I go to left, I've got some results with the PEU probe. So not a huge surprise. If you had done this on all 4 directions, we actually did do that. The same geometry, same pictures. Zoom in just a little bit more, and I'll pan just a little bit too. Okay, so I can go to SI results. These are on this tab, if you wanted to save them all, you can hit save results as SI results. These are going to save all your color maps, save calculated 2D functions if I wanted to. Go back to my data. Do I have something not selected properly, Raj?
Right click where it says name, right click, yes, and filter show all.
Okay. Oh, there we go.
Yeah.
I accidentally had filters. Okay.
Yeah.
Okay. Thank you, Raj.
Okay, no problem.
So here you can, that's what happened. I did another demo where you could add in columns, and I didn't realize I had everything filtered. It won't default to that in Test Lab, though. Here you can add in the different sides, and you can see where the intensity is. So at 400 hertz, it's very dominating on one side versus another. So we have one other example really quick. This is a motor that we've done, and you can see on all sides the intensity. I don't know if you can see this picture. You can kind of see the axis that it's spinning on. So, and I think we finished pretty much doing all the demo stuff.
So Steph, one thing which I wanted to mention was that with the PU probe, if you want to measure normal to the surface, you want to hold it vertically there.
Oh, correct. Sorry. It is hard to see where I am on the screen versus the probe measurements. That is correct. So
one comment regarding that, we did the discrete point measurements with the PP probe. We did the like point by point. There is the second ISO 9614-2 standard which governs the scanning method, and it requires that you scan 2 times, once along one direction and the time orthogonal to that, right? So if you take this surface here, the one where you see the red spot there, we will do the scan going from top to bottom, going from left to right. And another time you will go orthogonal to that. And the speed at which you should scan, that is governed by the field indicators for the data. If you scan too fast, like the field indicators will tell you, hey, you are scanning too fast. That is what in the intensity analysis worksheet, there is criterion for that. So it has to be checked against that.
If anybody has any questions at all, please feel free to email me, steph.nelson@siemens.com. Raj also is open for questions, and so is Charles. And thank you so much for being with us today.